Okay, guys. I think we should start. There are few of us, but we're strong. Okay. Well, today I want to discuss polynomials and several variables. So what is the difference between polynomials in one variable and polynomials in several variables? Well, in case of one variable, we can efficiently solve any task, basically because we have Euclidean algorithm, Euclidean division algorithm. So, for example, if you want to solve something, and you have a GCD of two polynomials, you know how to compute this GCD as a linear combination of two polynomials, and you can do this using extended Euclidean algorithm, and this is one of the main tricks for solving many tasks. In case of polynomials in several variables, there is an issue. You can prove that there is no division algorithm in the same way as it works in case of one variable. But still, we want to deal with polynomials in several variables efficiently. And there is some analogous procedure. It's called reduction. And in case of reduction, it looks like you divide with remainders, but in case of one variable, you divide just one polynomial by another one, and you will get one remainder. In case of several variables, you can divide one polynomial by a set of polynomials, and you will get one remainder. But this remainder need not be unique in general, and studying the properties studying the cases when this remainder is unique will be one of the main tasks for us. So, more or less, what I'm going to present is the theory of Grobner bases. And this theory is kind of analogy for the Euclidean division procedure. Okay. Polynomials in several variables. As usual, let's say f is a field. Then what is a polynomial in variables x1, xn? Well, it's a picture of the form, the sum over x1 to the k1, etc., xn to the kn, times a k1 kn, and the sum goes through all the numbers which are not negative integers. And also the amount of summands, non-zero summands, must be finite. So only finitely many coefficients are not zero. And this picture is called a polynomial in several variables. Now, this part of this polynomial is called monomial. This is the corresponding coefficient. And the whole summand is called term. So each polynomial in several variables is a finite sum of terms, and each term is a product of a coefficient from the field f and the product and the monomial, which is a product of powers of the fixed variables. Now, the set of all polynomials in variables x1, xn with coefficients in f is denoted by f x1, xn, like this. This is the set of all polynomials of this form. This set has two operations, which are addition and multiplication. So we have addition of polynomials and multiplication of polynomials in several variables. The addition and multiplication are given by the usual rules. And we can check that this set with these two operations is actually a commutative ring. Okay, now I want to start with some basic things. If we have a monomial, each monomial has a degree. The degree of a monomial is the sum of the degrees of its variables. So if we take a monomial, then its degree is just the sum of the powers of the variables. Now, the degree of the term is usually referred as the degree of the corresponding monomial. Now, if we have a polynomial, then each term of the polynomial has its own degree. Then we can take the maximum, and this is called the degree of the polynomial. So the maximum of all the degrees for all the monomials presented in the polynomial is called the degree of the polynomial. So if we take the maximum, this will be the degree of the polynomial. Okay. Well, for example, if we have something like this, qxy, and we take 2x squared y plus 3xy, then this guy has degree 3, this guy has degree 2, then the degree of the whole polynomial is 3 because this is the highest possible degree in the polynomial. Okay, what should be next? Yeah, and the property of the degree is the same as the property of the degree for the polynomial in one variable, which is the degree is additive. Okay. Now, well, when we have a polynomial in one variable, how do we divide with the remainder? Usually, we take the highest possible monomial in the divider, and then we kill all the monomials. Well, if we want to divide a polynomial f, let's say x cubed plus x plus 1, and we want to divide it by the polynomial x squared plus 1, what should we do? We should find the highest monomial here, and then we kill everything here using the highest monomial. How do we do this? Well, we just multiply this by x and kill x cubed. Then if we have x squared, we just multiply this by the corresponding coefficient and subtract again, and this is how the division works. Well, if we have polynomials in several variables, this procedure, well, it doesn't work, and the reason why it doesn't work is very simple. Well, if we have something like this, x squared plus y squared, then which one is higher? It's unclear, because, well, there is no way how to compare x squared and y squared. So we have to add some information in order to choose the highest possible monomial in this polynomial. And the way how to choose the highest possible monomial, well, is to choose what's called a monomial ordering. There are many different monomial orderings, but I want to be focused on one specific monomial ordering, which is called lexicographical ordering. So monomial ordering. So this is the way how to compare two different monomials in several variables. And I want to define the lexicographical ordering. Well, first of all, suppose we have the variables x1, xn. In order to define the lexicographical ordering, we need to define the order of the variables. So first, we need to specify which variable is higher than the other one. So here we have like n factorial cases. But for simplicity, let's assume that the order is chosen like this. I mean, in general, you can use any permutation, but just for simplicity, I want to have x1 to be the highest one, x2 to be the second highest one, and so on. Now, when the order of the variables is fixed, we can define lexicographical ordering for any two monomials. Let's say we have monomial 1 and monomial 2. Now we want to compare them using this information. So how do we compare them? First of all, we take a look at the highest variable, which is x1 in this case. And we compare the degrees of the highest variables. So we need to compare k1 and d1. There are three cases. The case number one, k1 is smaller than d1. And let's say this is a monomial m1 and this is a monomial m2. Just I want to give them a name. Okay, so the case number one, the first degree is strictly less than the first degree of the second monomial. In this case, we will say that the first monomial is smaller than the second monomial. In case k1 is strictly greater than d1, we will say that the first monomial is strictly greater than the second monomial. And there is the third option, where the first degree is the same as the first degree of the first degree of the first polynomial is the same as the first degree of the second polynomial. In this case, we should take a look at the second variable and compare the degrees of the second variable, k2 and d2. And again, we have three options. And if in this case the second degree is smaller, then the first one is smaller, the second degree is higher, then the first one is higher. If they are the same, we go to the next variable and we repeat this procedure until we go through all the variables. And if all the degrees are the same, then the monomials will be the same. So basically, we have a procedure which can compare two different polynomials using, or two different monomials using the order of the variables. Okay, who was able to follow the procedure? Okay, who think that I should repeat something or clarify the procedure? Okay, so let me be more specific. So formally, how to compare two polynomials, we say that two monomials, we say that the monomial m1 is smaller than monomial m2 if and only if there is an index I such that k1 is equal to d1, etc., ki minus 1 equals di minus 1, and ki strictly smaller than di. So this is a formal definition of being smaller. And this order is called the lexicographical ordering. And I will denote it by lex, x1, etc., xn, where the ordering here means that x1 is the highest one, x2 is the next highest one, and so on. So this is how to compare two different monomials. Just in case, an example. Suppose we have three variables, x, y, and z. By the way, do I want... Okay, let's say x squared y to the fourth. Which one? Oh, okay, it doesn't matter. Like z x cubed y z to the fifth. Let's say we have these two monomials. Which one is higher using the lexicographical order and this ordering of the variables? The first one or the second one? Which one is higher? The second one. What if I take these two? Okay, now it should be clear, I think. Okay. Now, what are the basic properties of the lexicographical ordering? There are three basic properties. The property number one, if we have a monomial and then this monomial is not smaller than 1, where 1 denotes the monomial where all the powers of all the variables are equal to 0. So, well, this is clear. And if m has at least one non-zero power, then it's strictly higher than 1. This is the first property. The property number 2, if we have a monomial m and a monomial, let's say, d, then m is not greater than m times d. And if d is not equal to 1, then the inequality is strict. Then m is strictly smaller than m times d. So if you take a monomial and multiply it by another monomial, then it can only be higher. It cannot be lower than the initial one. And the property number 3, if we know that m1 is smaller, let's say not greater than m2, and n is an arbitrary monomial, then m1 times n is not greater than m2 times n. So if you if you have some inequality and you multiply this inequality by the same monomial on the left and the right hand side, you will get the same inequality. So multiplication preserves this ordering. These are the properties. Just in case, who thinks that all these properties are clear? Is there anyone who thinks that at least one of them requires a proof? Okay, I hope, yes. Well, this should be clear just by the definition, or it's just a simple exercise. Now, there is a more interesting property. Well, let me formulate this one, the claim. Well, suppose we're given some lexicographical ordering, and we have a sequence of a strictly descending sequence of monomials. These are monomials. Strictly descending. Then this sequence must be finite. So it's impossible to find an infinite descending sequence of monomials. So if you have a descending sequence, at some point it must stop. Okay, so let me prove. Well, let's take a look at our sequence. Let's say we have m1 strictly small, then m2, which is strictly smaller than m3, and so on. So what is m1? m1 must be x1 to the power of k1 of 1, x2 to the power of k2 of 1, etc., xn to the power of kn of 1. Or this guy, I mean, in parentheses, means the index of the monomial. So this guy will be x1 to the power of k1 of 2, x2 to the power of k2 of 2, etc., xn to the power of kn of 2, and so on. Okay. Now, well, assume that the contrary holds. Suppose that there is some infinite descending sequence, strictly descending sequence of monomials. Now, and we want to get a contradiction. Well, if this sequence is strict, well, now, the first step, I want to consider the first variable of all possible monomials in this sequence. So if m2 is strictly smaller than m1, then what we have, k12 is not greater than k11. I mean, if this guy is strictly greater than this guy, then inequality here must be in the opposite direction. So because of this one is strictly smaller than this one, or they're the same. So in particular, it means that for the numbers k11, k12, k13, we have a non-increasing sequence of integers. And they are integers, non-negative. So what does it mean? If we have this kind of sequence, it must stabilize in the sense that at some point all these numbers must be the same, because there is no strictly decreasing sequence of non-negative integers. So there is some monomial, let's say mk, such that for all the monomials after the mk, the first degree is exactly the same. So there will be the same mr, let's say mr. I don't want to use the same letter because k is already taken here for the degree of the monomial. So let's say mr plus 1. So the first power will be the same. So now I want to take a look at the sequence of monomials starting from this mr. This sequence is also strictly descending because it's a subsequence of the initial one. But now all the degrees of x1 are exactly the same. So by the definition of the lexicographical ordering, if the degree of the first variable, if the degrees of the first variable are the same, then we can take a look at the second variable, and in this case, the degree of the second variable is decreasing sequence of integers as we had on the first step. So by the same argument, we can find some index here such that all the degrees of x2 will be the same. And then we can proceed to the third variable and so on and so on. So after finitely many steps, we will get that all the powers of all the variables must be the same. But this means that all the monomials starting from this step must be the same, which contradicts to the fact that this sequence is strictly decreasing. So this contradiction proves the result, because we assume that there is an infinitely long strictly decreasing sequence of monomials, and we've got a contradiction. Who was able to follow the argument? Is there anyone who requires some explanation, clarification, or should I repeat at least something? Okay. So that's why every decreasing sequence of monomials should stabilize. Now, there is one important remark. Let me show you one thing regarding the lexicographical ordering. Well, if we have two variables, a remark. If we have two variables, x and y, and x is higher than y, then if we take the monomial x, how many monomials are strictly smaller than x? Take a guess. Again? Just one.
Maybe as many as power of this monomial.
Which one? This? I mean, as many as. No. Well, no. Infinitely many. Let me show you.
So we can have negative powers.
No, we don't have negative powers. If x is higher than y, then by definition x is higher than y to the n. Because how do you compare these two monomials? You should compare the degrees of the highest variable. The highest variable here and here is x, just by definition. So the degree of x here is 1, the degree of x here is 0. So this guy is strictly higher than these guys. So there are, for each monomial, there are infinitely many monomials strictly smaller than the initial one. So, I mean, this explains that this fact is non-trivial, because if we fix a monomial m1, there are infinitely many monomials strictly smaller than m1. Then, if we take the next one, m2, there are infinitely many monomials strictly smaller than m2. So, I mean, in general, it's, you cannot use the argument that there are finitely many monomials smaller than m1. That's why it stabilizes, because it's not true, and this is an example. So be careful. So the reason why this is true is subtle. And this example explains this. Okay. So yeah, and you see, well, these are all possible monomials which are strictly smaller than x. But you see, there are infinitely many monomials strictly smaller than x. But if you want to produce a sequence, it cannot be infinitely long. Why? Because if you have x as the first monomial, then you should choose the second monomial. But when you choose the second monomial, it must be some specific power of y. Let's say y to the 10. And then there are finitely many monomials strictly smaller than y to the 10. And that's why you have to stop after finitely many steps. So, okay. Yep. Now I want to discuss the reduction procedure. So now, when we know how to find a highest monomial in a polynomial, I want to define the process of reduction. It will be very similar to the process of division in case of one variable. Reduction. Okay, so suppose we have a polynomial in n variables with coefficients in a field f. So f will always be a field. So now we can write this polynomial in the form where m1, m2, mn are monomials, and c1, c2, and cn are coefficients from f. And I can choose, well, since I know how to compare the monomials, well, if I choose a lexicographical ordering, let's say this one. There are n factorial lexicographical orderings, and I choose this one. It doesn't matter which one I choose. Well, the theory will work for any lexicographical ordering. Well, if I choose this one, then I know how to compare the monomials. So I may assume that m1 is the highest one, m2 is the second highest one, and so on. So m1 is strictly greater than m2, and so on. So we can rewrite each polynomial in this form. Okay? Now, in this case, this is the highest possible monomial. This is the highest possible coefficient, and this is the highest possible term. We have a specific notation for this guy. So m1 is just m of f, the highest possible monomial. c1 is c of f, the highest possible coefficient. And c1 m1 is t of f. is the highest possible term of f. And the rest of the polynomial is called the tail. So every polynomial, when we have an ordering, can be presented as the sum of the highest term and its tail. Now, I want to explain how to reduce one polynomial by another one. Suppose we have two polynomials, f and g. So these polynomials in variables x1, xn, and f is the field of coefficients. And I want to fix a lexicographical ordering. Let's say this one, just for simplicity. Now, I want to define an elementary reduction. Before doing that, let's say g can be presented in the form, which notation do I use here? I use this one. So it's the highest coefficient, the highest monomial, plus the tail of the polynomial g. Now, f, well, is in this form. C, let's say k, mk. Now, suppose here we have a monomial which is divisible by this guy. Suppose there is a monomial mi such that the monomial mi is divisible by mg. What does it mean? It means that it can be presented as mg times another monomial. So, what it means basically that for each variable, its degree is not smaller than the degree of the corresponding variable here. So suppose this thing can be presented as h times mg, where h is a monomial. Then, what I want to do, I want to multiply g by something and subtract from f such that the highest term of g will kill this monomial mi with the corresponding coefficient. So what should I do? I should take f and I should subtract what? G times what? I should divide by c of g in order to cancel this coefficient. Then I want to multiply by h in order to make the leading monomial of this polynomial to be mi. And then I want to have the same coefficient as here, which is ci. So if I do all this thing, then the highest monomial of this polynomial will be mi, and the coefficient, the highest coefficient of this polynomial will be ci. So when I subtract this, I will cancel the i'th summoned here. So this thing is called the elementary reduction of f by g. This is the elementary reduction of f by g. And the notation is the following. So we reduce f using g, and the result is f prime. Now, if we want to specify which one monomial was reduced, which one monomial here was killed, we can write this monomial down here, mi. Just in case, who was able to follow the procedure? of the reduction. Who thinks that we require an example? Okay, let me show you an example how it works. Okay, an example. Let's say we have how many variables? Let's say 2, x and y. And the coefficients are rational. Now, suppose f is x squared y plus x plus y squared. And let's say g is x, y plus 1. And the lexicographical ordering, well, here it doesn't matter, but let's say we have y, x. So y is higher than x. Just for this to be more interesting. Well, what is the highest term of f? Y squared. Y squared is the highest one. Because first, since y is the highest variable, we should check the power of the highest variable first. So here is the highest possible, so this guy is the highest one. And the highest term here is xy. Yeah, and let me write down some coefficients here because it won't be interesting without coefficients. Let's say 3 here and 2 here, okay? Now, so this is f, and this is g. So f has 3 summands, and g has the leading term and the tail. So this is the leading coefficient. This is c of g. This is the leading monomial, m of g. And this is the tail, g0, okay? Now, in order to make an elementary reduction, I need to find a monomial of f which is divisible by the highest monomial of g. Do we have such a monomial here? How many? Okay, is this guy divisible? Is this monomial divisible by this one? Yes, because we can represent this thing as this guy times x. Is this guy divisible by xy? No, because, well, you cannot multiply it by something and decrease the power of y. And can this guy be divisible by this one? Also no, because we cannot decrease the power of x. So that's why this is the only possible monomial that we can choose. So this is our monomial mi. Well, I mean, this is the term mi times ci. So mi is just the product of the variables. So in this case, so the monomial we want to reduce is x squared y. Now, what I want to do, I want to multiply this polynomial by a monomial and a coefficient in such a way that the highest monomial of the result will be exactly the same like this, and the highest coefficient of the result will be the same like this. Let's take a look. So we have 3 xy plus 1. Now, let's multiply it by x. When we multiply it by x, the leading monomial will be exactly what we want, okay? Now, but the leading coefficient will be 3, and we want it to be 2. So we need to divide by 3 and multiply by 2. So this is the formula that's written here. So this is h, this is c of g, and this is ci, okay? Now, if you open the parentheses, and 2/3, you will see that this thing is 2x squared y plus 2/3 x, Okay? So this thing is exactly the same as this thing. So now, if you subtract f minus 2/3 xg, you will cancel this monomial. So the result will be x plus y squared minus 2/3 x, which is 1/3 x plus y squared. So this is f prime. So now we can see that 2x squared y plus x plus y squared can be reduced using 3xy plus 1 to 1/3 x plus y squared. And the monomial that we chose to reduce was x squared times y. So we reduced this thing using this thing. And this is the monomial that was reduced here. And the result of the reduction is this thing. So this is how the elementary reduction works. OK, who was able to follow the example? Are there any questions regarding this procedure? OK, good. Now, when we have this elementary reduction, we can produce what's called a reduction. Again? Why do we add this? You see, if we don't have this, then we will get the coefficient 3 here. And when we subtract from f this expression without this coefficient, we won't kill this term. We will get minus 1 x squared y. But the idea of the reduction is to kill completely one of the summands of f. So we want to cancel these summand. So that's why we want to have the same monomial and the same coefficient. Okay? Because if you don't kill this monomial, it's not called a reduction, just an arbitrary procedure. But I mean, the whole idea of the reduction is to kill one summand of the initial polynomial f. And the other thing you should be aware of, when we want to kill this thing, we will kill this using the leading monomial of g. So, I mean, technically, you can multiply g by 2x squared y, and then the tail will be 2x squared y. Yep. And when you subtract, you will kill this monomial also. But this is not what we want to do. And the reason is the following. If you use the leading term to kill this monomial, what you do, you replace this monomial by the minus tail times something. But all the monomials in the tail times, in this case, x, will be strictly smaller than the monomial we had here. So in the process of the reduction, we take this monomial mi from the polynomial f and replace it by a sum of strictly smaller monomials. So if you try to reduce this thing using the tail, you will replace this monomial by the sum of something higher than the monomial mi. And we don't want this to do. The reduction must decrease the order of the monomial that was used. Okay? No, it's not a differential. It's just the name. Or let's say not f prime or like f1. It's not a derivative. It's not a derivative. No, it's just a name of a polynomial, which we get. Okay, but the main goal is to define a procedure which is similar to a division with remainder. So that was just one step of the division process. Now I want to define the whole division process, and I want to define a remainder, and I want to discuss the properties of the remainders in this particular case. So we will get some anomalies in case of several variables, and you should be familiar with these anomalies. Let me show you. Now, let me see. Do I need to define something here? This guy, then a remark, and a okay. Now, the next definition, a reduction. So again, when we have two polynomials and we have a lexicographical ordering, so you cannot make a reduction without having an ordering. So you have to say which ordering you use, because if you change the ordering, you will change the process of the reduction. Because, well, in this case, it doesn't matter which ordering you use, this guy will be the highest possible monomial. But if you take something like x plus y, well, the leading monomial will change, and the whole process of reduction will change. So again, so an example, so if g is x plus y, then in case of this, well, then we have two lexicographical orderings, and with respect to this ordering, the leading monomial is x. But with respect to this guy, the leading monomial is y. So if you choose a different order, you will, you will get a completely different reduction procedure, because you'll have to reduce with a different term. Now, if we have two polynomials f and g, and let's say g is not 0, now, what is the process of reduction of f by g? A process of reduction of f by g is a sequence of elementary reductions. So if we have a sequence of elementary reductions, this will be called just a reduction of f by g, and we will denote it like that. This is just a reduction. Okay? Now, in case of polynomials in several variables, it makes sense to reduce one polynomial by a set of other polynomials. So the second thing, suppose we have a set of polynomials. Well, we actually may have an infinite set, but in this case, let's assume we have just a finite set. It doesn't matter which one. Then I want to say that we have a reduction of polynomial f by the set g, and we will get fk if we have a sequence of elementary reductions of f using the elements from g. So it means that we have something like this. Where, let's say, like that, where gi1, gi2, etc., they are the elements of g. So it may happen that we have a set of polynomials, g1, gr, and then we take a polynomial f, and we make several elementary reductions using different polynomials from g. And then the result of this sequence of elementary reductions is called a reduction of f by the set g. This is just a generalization of this process when you can use several polynomials as a divider. Okay, so what is the remainder? In this case. So what is the remainder? Well, suppose, okay, let's define it here, the definition, a remainder. Well, if we have a polynomial f and its reduction to a polynomial, let's say h, and suppose it's impossible to make at least one elementary reduction of the polynomial h. So for every g, it's impossible to make an elementary reduction. For every g from g capital, it's impossible to make an elementary reduction of the polynomial h. What does it mean? It means that every term, every monomial of the polynomial h is not divisible by the leading term, by leading monomial of every polynomial from g. So you cannot find this kind of monomial. So this is what it means here. So then, in this case, we will say that h is a remainder. So basically, what you do this sequence of elementary reductions until it's possible, and when it's no longer possible to proceed, what you get is the remainder. Now, there are several questions to ask. Can you try to guess which one?
How many such?
That's a good question. First of all, how many different remainders do we have? Is it true that we have at least one remainder? Because in case of Euclidean division, it's true that, well, it doesn't matter how to divide your polynomial, the result will be the same. Well, but there is another interesting question. Is it true that this process will terminate? I mean, is it possible that you may have a polynomial f and a set g such that you perform these elementary reductions and you will never stop? I mean, hypothetically, it may be possible that, well, you can find such a terrible polynomial and such a terrible set that you will never get a remainder. But this is impossible, actually. So there are two things. There are two remarks. Remark number one. I will prove all of this. So the reduction process will terminate. So you will always get a remainder. So if you start reducing, you will get to the remainder. The second thing, it's possible to have several remainders. The remainder need not be unique. So let me show you an example when the remainder is not unique. Okay, so an example. Let's take Q, X, Y, Z, and the lexicographical ordering where X, Y, Z are going in this order. X is the highest one, and so on. Now, I want to take F to be X, Y, Z, the product of the free variables. Then G1 is X, Y minus 1, and G2 is Y, Z minus 1. And the set G capital will be the union of G1 and G2. By the way, if the set G consists of one polynomial only, then the remainder will be always unique. We will prove this. So the simplest possible example when the remainder is not unique consists of the set G containing two polynomials. Now, what is the leading term here? Well, the leading term here is xy, and the leading term here is yz. And the only term here is the product of x, y, z. So let's make a reduction of f using g1. So if we take x, y, z minus x, y minus 1, so we want to multiply this thing by z in order to cancel x, y, z. Okay? So this is the process of elementary reduction, and the result will be z. So this is a remainder because you cannot divide z by neither of these guys. Now, let's reduce f using G2. So we should subtract yz minus 1. And in order to cancel this thing, we should multiply it by x, and the result will be x. And this is also a remainder because you cannot proceed with the reduction procedure. So here we have two different remainders. So this is an example when you can reduce a polynomial by a set, and you will get two different remainders. So it's possible to have this anomaly. Now, but the reason why we have two different remainders is because this set was bad. This guy is bad. He's a bad boy. So we want to replace, well, actually, if you take a look at all possible sets G, you can divide them into categories. The bad ones and the good ones. The bad ones are those sets where you have at least two different remainders for at least one polynomial, and a good set when for every polynomial f, all the remainders are the same. And this leads to the definition of the Grobner basis. Let me define the Grobner basis. The definition. Well, okay, we have this ring of polynomials, so any field, several variables. We have a fixed lexicographical ordering, and G is a set of polynomials. Well, we actually want them to be non-zero, so I want to exclude the zero polynomial. Now, I will say that G is a Grobner basis. Yes, that's a German word. If the following property is satisfied. For every polynomial f, all the remainders of f are the same. What does it mean exactly? It means that if you have your any polynomial f, like absolutely arbitrary polynomial from this ring, and you take a sequence of elementary reductions leading to one remainder, and another sequence of elementary reductions leading to another remainder. This guy, a remainder, and this guy is a remainder. Then, and all of these polynomials gi from the set G capital, then these two remainders must be the same. I mean, this is just a clarification for this phrase of the definition. I mean, I just reformulated it in explicit form. So a Grobner basis is such a good subset of non-zero polynomials such that you will always get exactly one remainder. And an example of a Grobner basis, well, I cannot prove it now, but I will be able to, probably during the next lecture, that if we take a set containing just one polynomial, it will always be a Grobner basis. Well, I mean, there are examples of Grobner bases containing several variables. I think it does matter what are they, because we don't know the criterion for a subset for being Grobner basis. So we will discuss it during the next two lectures. So I don't want to present them now. But at least you should be aware of that. If you take just one polynomial, the notion of remainder is well defined. So you will always get just one remainder. You shouldn't be worried of some anomalies. Okay, we have 20 minutes, and I want to prove that the reduction process will actually terminate. But before doing that, should I mention anything else here? Oh, there is another example of Grobner basis which should be clear even right now. Let me take a ring with 4 different variables, okay? Now, so let's take polynomials like this. So in this case, and the lexicographical ordering doesn't matter which one, because these guys will be the leading terms. But in order to be more specific, I just want to fix some lexicographic ordering. Now we take a look at the leading terms, and you can see the leading terms, their monomials have distinct sets of variables. The sets of variables here and the set of variables here, they do not intersect each other. In this case, this is also a Grobner basis. So this is another simple case when a set form a Grobner basis. Okay, but there are many other cases when this is not true and they're still Grobner basis. Now, okay, so okay, so now what I want to do, I want to show you that if you have a sequence of elementary reductions, this process will always terminate. So you will always get to a remainder after finitely many steps. Okay? In order to do this, I need one auxiliary definition. So if we have a polynomial, and we have some lexicographical ordering, and we can rewrite our polynomial in this case, in this form, where m1 is strictly greater than m2 and so on, and mk, I want to denote mk as mk of f, ck as ck of f, and the product ck-mk as tk of f. So basically, m1 is the first highest possible monomial, m2 is the second highest possible monomial, and so on and so on. I just want to use this notation during the proof of the claim. Now, before proving the main claim, I want to prove some auxiliary statement, and then I will prove that the reduction will always terminate. Okay, well, an auxiliary claim. Suppose we have, let me see how many statements are there. Okay, I have 3 polynomials. I want to reduce. That's it. So suppose I have 3 polynomials. have a fixed lexicographical ordering, so I can't produce a reduction. And suppose f prime is a reduction of f by g. And suppose that the leading monomials of f and m prime are the same up to some index k. Let's say k minus 1. Okay? And the monomials mk of f and mk of f prime, they exist. Then mk of f is not smaller than mk of f prime. So let me explain what's written here. So suppose you have a polynomial, and it has its monomials sorted in a decreasing order. Then you make a reduction of f, and suppose the first k minus 1 monomials remains the same in the reduction as here, and you still have something else. And then when you take the highest possible monomials in this something else, then in the reduction, this highest monomials of the tail is not greater than the highest monomial of the tail of f. This is what I'm claiming. Okay, are there any questions regarding this statement, the statement of the claim? Who thinks that the statement of the claim is clear, what it means? Not why it's true, but what it means. Okay, who thinks that it requires a clarification? Okay, so let me do the following. I will try to prove this, and during the proof, I will try to clarify the statement itself, okay? So you will see how it works. Well, suppose I have a polynomial f, and it has this form. Okay? So I have sorted all the monomials of f in a strictly decreasing order. So this is the highest one, this is the kth minus 1 highest one, this is the kth highest one. Now I want to write down the polynomial f prime, which is a reduction of f. So it's c1 prime and 1 prime plus etc. plus ck minus 1 prime mk minus 1 prime plus ck prime mk prime plus probably something else. And we know that f prime was a reduction of f with respect to g. Okay? Now, what this says, it says that the leading monomial of f is the same as the leading monomial f of prime. So we can erase prime here, okay? Now, all these equalities mean that the monomials with numbers from 1 to k minus 1 are exactly the same. So these monomials are the same, okay? Now, and we know that these monomials exist. And what I want to prove that mk is not smaller than mk prime. So this is what we want. So if this guy was obtained as the reduction of this guy, and these monomials are the same, then for these monomials, if they exist, we have these comparison. Okay? So this is what so this is the claim. Okay, now who thinks that the claim becomes clear? Okay. Now, well, let's recall. What does it mean that we have a reduction of f by g? It means that we have chosen a monomial here, and we killed this monomial, and we replaced this monomial by the tail of g times something. But in any case, we replaced a monomial by a sum of strictly smaller monomials, okay? So based on this, I claim that we didn't reduce m1 mk minus 1. Why? Because let's say if we reduced m1 then after reduction, the highest monomial of f will be changed. So it's impossible to have the highest monomial of f prime the same as the highest monomial of f. So we didn't touch m1. Who was able to follow? Are there any questions, or should I repeat this? Was it clear? Okay, so again, what is a reduction? How do I do a reduction? So I choose a monomial in f, okay? Then the polynomial g is represented as the leading term of g plus its tail. And then I subtract some from f the polynomial g times some coefficient and times some monomial in such a way that the monomial I chose is cancelled by the leading monomial of the resulting polynomial here, okay? But what remains, as you can see, what remains is I replace the monomial I reduced by the product of ch and g0. Okay? But since all the monomials here are strictly smaller than this guy, then after multiplication by h, all the monomials in g0 times h will be strictly smaller than this monomial, which coincides with the one we reduced. Okay? So that's why after this procedure, if we reduce this monomial is replaced by a sum of strictly smaller monomials. Okay? So in particular, the leading monomial after reduction will be strictly smaller than the initial monomial. So this contradicts this assumption. Okay? So in the same way, we didn't touch any of these monomials from 1 to k minus 1. So reduction was actually done somewhere here. So the monomial that was taken for this reduction leaves somewhere here. Now there are two options. This monomial is either this one or it lives here. Well, if it lives here, then we replace this monomial by the sum of smaller ones. So the kth monomial remains the same. So in this case, mk and mk prime are exactly the same. And if we reduced the monomial mk, then we replaced it by the sum of smaller ones. So the mk prime must be something smaller than mk. So in this case, mk prime is strictly smaller than mk. So that's why if we reduce something here, then indeed the kth monomial is either the same or strictly smaller. Who was able to follow? Okay, good. Now we're ready to prove that the reduction process terminates. Okay, so the claim, suppose we have a polynomial ring with some fixed lexicographical order. We have a polynomial f and some set g. And suppose we consider a sequence of reductions. So then this sequence terminates. So, I mean, at some point, it's no longer possible to make a reduction using polynomials from G capital. And by the way, G1, G2, G3 doesn't mean they are distinct. I mean, we can use the same polynomial G from G capital to reduce several times. I mean, you don't need to use distinct polynomials at all the steps. Now, let's assume that the contrary hold. Assume not. Then we have an infinite sequence of reductions. Let's take a look at the leading monomials of these polynomials. So we should take a look at the leading monomials of this sequence. Okay? Now, well, since the sequence is infinite, leading monomials, they exist. Like for every polynomial here is not 0, because if we have a 0 polynomial, then we terminate. Now, using this claim, in case k to be 1, so the set of equalities is just empty, we know that the leading monomials, well, they form non-increasing sequence of monomials. So that's why we have a non-increasing sequence of monomials. Well, since we know that there is no strictly decreasing sequence of monomials, there must be a step such that after this step, all the leading monomials are the same. Because if there is no such a step that all the leading monomials are the same, then we can find a strictly decreasing sequence of monomials. But we already know that there is no strictly decreasing sequence of monomials for the lexicographical ordering. So there is an index, let's say R1, such that the leading monomials of all the polynomials will be exactly the same starting from this point. Okay? Now, after this point, we should take a look at the second highest monomials of the polynomials. R1 plus 1, M2 of R1 plus 2, and so on. Now, again, using this claim for k to be 2, we have just one equality, and we know that the second highest monomial must exist, otherwise this sequence is stationary. So that's why, by the previous claim, again, we have a decreasing, not necessarily strictly decreasing, but a decreasing sequence of monomials on the second place. But starting from this point, not earlier. Starting from this point, the second monomials form a decreasing sequence. And again, since we do not have a strictly infinite, strictly decreasing sequence, this sequence must stabilize. So from some step, we have a sequence of equalities. So there is R2, such that starting from R2, all the second monomials are the same. And we can proceed, and we can produce these sequences of stable monomials. Now, let me show you where the contradiction comes from. So this procedure will never stop. Because of this argument, we can go to the third highest monomial, then to the fourth highest monomial, and so on, and so on, and so on. And we can repeat this argument infinitely many times. Like as many times as we want. So after this, what do we have? We have, first of all, we have this leading monomial where we have stabilization from the first case, okay? Now, then we have the second highest monomial where we have this stabilization. But since this guy is not greater than this one, and this was the second monomial in this polynomial, so this guy is strictly smaller than this one. So we have this comparison here. So just by the choice of the monomials, the monomial here is strictly smaller than the monomial here. And if we repeat this procedure, we will get M3 of f for some step R3, which is strictly smaller than M2, and so on. And since this sequence was infinite, and this argument works on every step, this sequence is also infinite. But now we have a strictly decreasing sequence of monomials, which is infinite. And this is a contradiction. So that's why, and this is impossible. And this is a contradiction. That's why our assumption was not true. So that's why this sequence must be finite. Who was able to follow? Okay. Should I repeat? Okay, so again, what is an idea? So let's take our polynomial. It consists of several monomials, okay? Let's start to reduce this polynomial. First of all, we take a look at the highest possible monomial. It decreases, decreases, decreases. At some times, it remains the same. Okay, the highest possible monomial in our polynomial. Now, when the highest possible monomial is the same, we take a look at the second highest possible monomial, okay? It could decrease, 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 and then it remains the same. So now, the two first monomials of all the reductions are the same. So we take a look at the third possible monomial. It reduces, reduces, and after several steps, it becomes the same. So that's why we will produce a sequence of monomials, and the sequence of monomials will never stop. And they will be smaller, 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 smaller. So that's why we will get a strictly decreasing sequence of monomials. And this is a contradiction because for the lexicographical ordering, we do not have a strictly decreasing sequence of monomials. It must stabilize. That's what we proved like at the beginning of the lecture. Was it clear now? Okay. Are there any questions? Okay, again, now, who think that the proof was clear, just in case? Are there any questions regarding the proof? Okay, that's it. So let me summarize what is happening today. So we discussed polynomials in several variables. In order to compare the monomials of these polynomials, we define a lexicographical ordering. There are several different lexicographical orderings. They depend on the choice of the ordering on the variables. And now, using any lexicographical ordering, we can reduce one polynomial by another one. And we proved that the process of reduction, if you apply several reductions, it will always terminate in the sense that you will always get a polynomial which is no longer reducible by the set of polynomials you have chosen. And this polynomial is called a remainder. And the main anomaly of this process is that if the set G you have chosen for the reduction is not good enough, then you may have many different remainders. So a remainder may depend on the sequence of reductions. And if the remainder doesn't depend on the sequence of reductions for any polynomial f and for any sequence of reductions, then the set G is good enough, and by definition is called a Grobner basis. Just in case, Grobner is a surname of a German mathematician. One last question. Who do you think invented Grobner basis?
Not a Grobner.
That's a good guess. Well, actually, Buchberger was an inventor of the Grobner basis. Grobner was his mentor, and in honor of his mentor, he named his invention as a Grobner basis. But later, the algorithm, one of the main algorithms of this theory was called a Buchberger algorithm. So, it's not a big deal that somehow he donated one of the results. Okay, are there any questions before we stop? Okay, then that's it. Thank you for being here, guys.